Hi everyone, I'm Kathleen Wage and I'm back with another array processing video. This video explores the analogy between discrete time, linear time invariant filters, and uniform line array beamformers. This analogy is really key because it's going to allow us to leverage all that we know about discrete time FIR filters and apply it to the concepts and the processing we're learning in terms. This analogy is key because it's going to allow us to leverage everything that we know about discrete time FIR filters and apply it to the concepts that we're learning about uniform line array beamformers. From digital signal processing or any discrete signals and systems course, we know that a discrete time system, LTI system, can be characterized by its impulse response, h of n. And we can relate the input and the output of the system through a convolution with that impulse response. Similarly, we can work in the transform domain, and here I'm using capital omega as my discrete time frequency variable. And so I can relate the output Fourier transform of the output of the filter is y of e to the j omega, and it's the multiplication of the input Fourier transform x of e to the j omega with the frequency response h of e to the j omega, which is simply the Fourier transform of the impulse response. So if we look, the impulse response and the frequency response are two key things that we use to characterize discrete time FIR filters. In the world of narrowband uniform line array beamforming, the weight vector and the beam pattern play similar roles. So here I'm assuming that the input measurement vector, input vector of narrowband measurements, is a vector x, and it gets processed by the narrowband beamformer. So the beamformer computes W Hermitian x, where W is the weight vector. The weight vector plays a similar role to the impulse response. And we can similarly relate the Fourier transform of the output that we get, y of e to the j psi, will be the beam pattern, which is the spatial frequency response, times the Fourier transform of the input, characterizing the input. Here I'm using the variable psi as my discrete frequency variable, and it's defined as the vertical wave number, kz, times d, and there's a minus sign, so a sign change there. D is the sensor spacing. So we're going to try and see how we can apply what we know about this problem to understand the uniform line array beamforming problem. So let's start by reminding ourselves of a few key things about discrete time LTI filtering. We're starting with a sampled signal x of n. We process it with our LTI filter, we get an output y of n. The input and output are related through discrete time convolution, right? So y of n is h of n convolved with x of n, and I've simply written the convolution sum here, right? Where I've assumed I'm flipping h and doing the standard discrete convolution calculation. If I take the Fourier transform, this convolution turns into a multiplication. Specifically, the Fourier transform of the output, y of e to the j omega, is equal to the Fourier transform of the impulse response, which is the frequency response, h of e to the j omega, times the Fourier transform of the input. Okay, and just to remind you, this is a sampled signal here, meaning that Fourier transform is actually a discrete time Fourier transform, which is periodic with period 2 pi. So I can compute the output y of n as simply the inverse transform of y of e to the j omega, and I've written the standard inverse transform formula here. Well, suppose all I want is a single value of that output. If all I want is a single value of the output, and suppose I happen to want the value at time 0, then I just substitute in n equals 0 here, meaning that this complex exponential just becomes 1. And now I'm just looking at 1 over 2 pi, the integral from minus pi to plus pi of y of e to the j omega d omega. And I can substitute in the multiplication of the frequency response and the input transform here. Okay, so if all I want is the output at a single time point times 0, this is what I can calculate. Similarly, I could evaluate my convolution sum at a single time point at 0, and so I just plug in n equals 0 here, and I end up with this summation. If my filter is a finite impulse response filter, then this will turn out to be a finite sum, right? In general, the convolution is an infinite sum, but if the filter is FIR, this will be a finite sum. All right, so this is all straightforward from standard discrete time LTI filtering. So before we move on to look at the beamforming analogy, let's just consider a simple example. Suppose that we have complex exponential inputs. So I put in two complex exponentials, one with frequency omega 1 and one with frequency omega 2, to a linear time invariant system with this frequency response. Remember, the frequency response is periodic with period 2 pi, but I'm only drawing one copy, the copy between 0 and 2 pi. So we can solve this. We're going to try and solve for what is the output at time 0, right? So what is y of 0? So we can solve this by working in the frequency domain. And first we find the Fourier transform of these exponential signals. Well, that's straightforward to do from our experience with discrete time signals. We know that complex exponentials have transforms that are equal to delta functions. So what I would get for the transform of the first one is 2 pi a1 delta of omega minus omega 1. So that's a delta function at frequency omega 1 scaled by 2 pi a1. And the transform of the other piece is simply 2 pi a2 delta of omega minus omega 2. So that's a delta function at omega 2. So I can just sketch that over here. Let's assume omega 1 is here. Let's assume omega 1's there, and this is 2 pi a1. And let's assume omega 2 is here. And so 2 pi a2 is there. Okay? In general, a1 and a2 are complex. I'm just drawing them as if I'm drawing real numbers here. So now I can use my formula that I derived on the previous page to find y of 0, right? So I can just say y of 0 is going to be equal to 1 over 2 pi, the integral from minus pi to plus pi, y of e to the j omega, d omega. Well, that's the same as 1 over 2 pi, the integral from minus pi to plus pi, h of e to the j omega times x of e to the j omega, right? Because that's my equation for y, d omega. Okay, well, it's straightforward to multiply the delta functions by h of e to the j omega, right? I'm going to get 0 everywhere except at the delta function, and then the delta function is going to be scaled by whatever the value of the frequency response is at the frequency of the signal. So I'm going to get 1 over 2 pi, the integral from minus pi to plus pi. It'll be 2 pi a1 times h of e to the j omega 1. That is the value right here. And then it's still a delta function, delta of omega minus omega 1, plus 2 pi a2 h of e to the j omega 2, that's the value here, times delta of omega minus omega 2. And we're going to integrate with respect to omega. Okay, so I'm integrating something that consists of two delta functions. Well, this is just a scalar, right? The scalar in front of the delta function represents the area of that delta function, right? So I'm going to get the area here and then normalized by the 1 over 2 pi. So the 2 pi's are going to cancel. I'll end up with a1 h of e to the j omega 1 here for this term. And then for the other term, I'll end up with a similar thing. It'll be a2 h of e to the j omega 2. Okay, I'm expecting a scalar, right? I'm just calculating the output at a single time point, y of 0, and I get a complex scalar, that is a1 times the value of the frequency response at omega 1, and a2, the amplitude of signal 2, times the frequency response at the frequency of that signal, omega 2. All right, so this is how I can use what we just reviewed to calculate the output when I just have complex exponential inputs. Okay, so now we're going to try and use that analogy that we just refreshed our memories about and apply it to the ULA beamforming problem. So a ULA beamformer, instead of being a time invariant system, now because it's a spatial filter, it's a shift invariant system. And remember, it takes an input vector x, that's the measurements of the narrowband signal at the array, and applies a weight vector w and computes the output w Hermitian x. And we can write this as a summation, right? This is just the inner product of a weight vector and the input vector. So I can write that summation as the sum L equals 0 to n minus 1, w conjugate of L, because of the Hermitian there, times x of L, right? I'm assuming, right, that this is an n minus 1 point ULA, right? So I have n minus 1 sensors. That's my assumption. Okay, well, this equation here looks a lot like the equation for the output of that discrete time LTI system at a single time point 0, right? It looks a lot like y of 0, and it'll be exactly equal to y of 0 if we make h of minus L equal to w conjugate of L, right? H of minus L was what showed up. This was the formula we got out of that convolution. And if we equate these two, right, if we equate w conjugate of L with h of minus L, then we have the same system. So this essentially looks like an FIR filter with h of n defined to be w conjugate of minus n, right? So great. Now, if we have an FIR LTI filter, then we know convolution holds. Y of n will be equal to the convolution of h and x. And then y of e to the j psi is equal to h of e to the j psi, x of e to the j psi. Again, I'm using psi as my discrete frequency variable here because I want to emphasize that it's different, right? It's the spatial frequency variable instead of the temporal frequency variable. All right, but the system is basically the same setup, okay? Now, I know how to calculate the Fourier transform, h of e to the j psi. That is, the standard formula for that is the sum over all n of h of n e to the minus j psi n. This is just the standard discrete time or discrete space Fourier transform. Okay, and I can rewrite that. I'll just substitute in, instead of h of n, I'll substitute in my weight vector, right? The equation for my weight vector. So I'm substituting in w conjugate of minus n e to the minus j psi n, right? So all I'm doing is making this substitution into here. Okay, now I can rewrite this summation a bit just by assuming L is equal to minus n. So I'm going to sum over a different variable now. Okay, so now this will be the sum, L equal, and ignore the limits here for a second, right? But I'm just flipping the sign, right? So this will be the sum of w conjugate of L, right? E to the j psi L, okay? And we know that I only have, I only have n weights. Actually, I made a minor error here. It's an n sensor ULA, not n minus 1 sensor ULA. So, all right. So I'm summing over my endpoints here. All right. So the frequency response, h of e to the j psi, is just this summation, right? And I've had to make a change of variables, but that's the same summation. And you'll recognize from other videos we've done, this is the beam pattern. This is the beam pattern, okay? This is exactly how we've defined the beam pattern. So the beam pattern is the frequency response of our shift invariant filter. Thus, we can say for a uniform line array beamformer that the output, the Fourier transform of the output as a function of the spatial frequency variable psi, yv to the j psi is just the beam pattern b of v to the j psi times x of v to the j psi, where that's the Fourier transform of the input. Similarly, I can now just apply the formulas I did before to calculate y of 0, the output at n equals 0, right, is 1 over 2 pi, the integral from minus pi to plus pi, of the beam pattern, b of v to the j psi, times x of v to the j psi, and I'm integrating with respect to psi. This is the equivalent to W Hermitian x, right, which is how we calculate the output of the beamformer. And again, the output, this is the output of the beamformer. It's a scalar output, and it's really the value that we get at the phase center of the array. The phase center is defined as the n equals 0 element, which in our case corresponds to the z equals 0 element. And again, I just want to emphasize that the spatial frequency variable here that I'm using is psi, and it is, we've defined that more generally to be equal to the vertical wave number kz times the sensor spacing d with a minus sign. Okay, so now let's see an example for the beamforming context, right? So let's assume that our x of n, our input, consists of two complex exponentials again, right? So x of n, we would say in this case, is equal to a1 e to the j psi 1 n plus a2 e to the j psi 2 n. And I just want to emphasize this is basically, right, the complex exponential in the space domain. This is a sum of two plane waves. The plane waves are the complex exponentials. And I can compute the angles associated with those plane waves given the vertical wave number. Okay, so I have an input that's a sum of two plane waves, a sum of two complex exponentials, which means that the input spectrum looks like a line spectrum. It contains two delta functions. So now I can do what I did before and say, well, what is the output of the beamformer when I apply the weight vector W, right? When I run it through a beamformer with a system that has the weight vector W. Well, that simply will be 1 over 2 pi, the integral from minus pi to plus pi of the beam pattern b of v to the j psi times x of v to the j psi d psi. Again, these are delta function spectra, right? So we just multiply this way, and then we integrate, right? This is exactly the same type of integration we did before. So what we're going to end up with is a1 b of v to the j psi 1 plus a2 b of v to the j psi 2, right? So the amplitude of each of the plane waves gets scaled by the complex value of the beam pattern at the frequency associated with each of those plane waves. So this is basically the frequency domain interpretation of these results. I can have a spatial domain interpretation of these results, right? It's W Hermitian x. Well, now x is equal to a1 v of psi 1 plus a2 v of psi 2, right? The measurement vector x that we would get is simply, we can write it in terms of the narrowband replica vector, right? The narrowband replica, where v is a narrowband replica vector. It's a complex exponential vector, right? And it is associated with a particular frequency, in this case psi 1, and in this case psi 2. So the output here is this, and so I'll get a1 W Hermitian V of psi 1 plus A2 W Hermitian V of psi 2, right? Okay, well this I easily recognize from our other work as just the beam pattern evaluated at psi 1, and this is the beam pattern evaluated at psi 2, right? This is exactly what I got up here, but this is just a way to view it in the space domain interpretation where we're just doing the inner product of the weight vector with the exponential vector that represents each of these two signals and adding them together. Again, all of these are complex quantities. A1 is complex, B in general is a complex number, A2 and B of psi 2 is also complex. I just wanted to briefly mention that my definition for the narrowband replica vector. So the narrowband replica vector, we can write it as a function of the wave number kz, and if we're assuming an n-element ULA with spacing d, meaning say z goes in this direction, I have the first sensor at 0, the second sensor at d, 2d, etc. I can so then my narrowband replica vector looks like this. It's just the complex exponential e to the minus j kz d times times wherever the number of the sensor. If I use my definition for psi as minus kzd, then this narrowband replica as a function of psi is e to the plus j psi times little n, where little n is the entry in the vector. This is the 0th entry, this is the n minus 1 entry. All of this agrees with the sign convention in optimum array processing by Van Trees. So I hope that this video has shed some light on this key analogy between discrete time LTI filters and narrowband uniform line array beamformers. That way you can use a lot of the intuition you have about discrete time LTI systems and apply them to what you're learning about the standard narrowband uniform line array beamforming system. So that concludes this video. Again, I'm Kathleen Wage. If you want more information about this class or other information, you can contact me at my email here. And this video was produced using the Viddle Pro software for the iPad. Thanks for listening.